First of all, thanks very much for all of you who are attending the session, and thanks so much to the organizers for inviting me. And thanks, Mark, for giving me a round of applause before I started. Very grateful. So the Andre-Pink, so everything I talk about is joint work with Josh Lam. Okay, so the Andre-Pink Zannier conjecture is about how isogeny orbits are distributed in Shimura varieties. So let me just start off with some broad results that are true over C. So let S be a Shimura variety. Soon enough, I'll specialize to the case of AG, but for now, let's just say some Shimura variety. Once you impose fairly minor restrictions, you have this really beautiful theorem by Clauzel, O, and Ulmo, which tells you the following. So let X be a point. Shimura varieties are equipped with correspondences called Hecke correspondences. So let tau I be a sequence of Hecke correspondences with degree going to infinity. Then the set tau I of X, so you take X, you hit it with tau I, you let I go to infinity, this set equidistributes in S. Right, so in particular, tells you that if you were to take a Shimura variety, take any sort of ball inside it and you holomorphic open, and then you take a point and you keep iterating various different Hecke operators, then eventually you will enter the ball. You can't avoid a positive volume subset of the Shimura variety for every Hecke operator. Okay. So let me just say this as Hecke orbits intersect complex opens of Shimura varieties. Well, you might want to ask other distribution questions. For instance, let D contained in S be a subvariety. Then can you find a point of S which, even after iterating with every single Hecke operator, avoids your subvariety D? So if you ask this question over the complex numbers, then it's an easy question to answer for the following reason. Your Hecke correspondences are sort of, well, the correspondences, and there's countably many of them. Asking this question is the same as asking whether you don't start off with X, but start off with D. Now you move D around by every single Hecke operator. Take the union. Do you get all of S? Now, every tau I of D is going to be a subvariety of S. There's countably many subvarieties. So the union is going to be measure 0 and therefore can't be everything. And so you can find an X which avoids D even after applying all Hecke operators. So this question actually has a very interesting history. This precise formulation of the question in other settings is due to Bjorn Kuhnen. So this question was originally asked in the following setting. So let's specialize to the case of AG, which is the moduli space of polarized abelian varieties. And let's take D to be the Jacobian locus. Then this question is equivalent to asking whether you can find an abelian variety that's not isogenous to a Jacobian. And this question was asked by, I think, Oort, Katz, and Bjorn was the one who came up with this formulation in terms of just taking an arbitrary subvariety of a Shimura variety and asking whether you can find a point that avoids a double isogeny. And this extremely simple argument tells you that, yes, if you are asking for an abelian variety with the complex numbers, then yes, you can find one that's not isogenous to any Jacobian. The question is harder over Q bar because countability arguments just don't cut it anymore. Everything is countable. It's still a theorem due to first proved by Chai, Oort, conditionally, and Zimmerman, who relaxed conditionality. Also later by Masser and Zannier using O-minimal techniques, and also in joint work with Zimmerman using intersection theoretic techniques that tell us that there is an abelian variety over Q bar that's not isogenous to any Jacobian of every dimension of dimension any G that's at least 4. All right. So this question is not that related to the Andre-Pink Zannier question, but then once I start talking about this question, once I start talking about things in characteristic P, it'll hopefully become a bit more clear why I've brought up this seemingly unrelated question. But in any case, both Closello and Olmos theorem, as well as questions like this, address the question of how Hecke operators and Hecke orbits of points are distributed in a Shimura variety. So now let me ask the actual question that we're going to be concerned with, namely, can you have a subvariety of a Shimura variety that intersects some Hecke orbit in a big set? And by big, I mean in a Zariski dense set. Well, the answer is, of course, yes. For instance, the whole Shimura variety itself, you take any point, you take its Hecke orbit, it's equidistributes, and therefore has to be Zariski dense. So let me rephrase this question and say, when will a subvariety of S intersect some Hecke orbit in a Zariski dense set? And like I said, any S itself, let's call the subvariety Z. So let's say it's called subvariety V. So V equals S is one such example. Now, any Shimura subvariety of V will also satisfy this property because you can take a point of the Shimura subvariety. Don't look at all Hecke, don't look at the whole Hecke orbit. coming from S, but look at those Hecke correspondences that just come from the smaller Shimura variety. That's going to be dense in the smaller Shimura variety. And when I say Shimura subvariety, what I mean is an irreducible component of such an object. But there are other sorts of spaces that also intersect Hecke orbits in a dense set. So let me give you an example. Let's take the Shimura variety to be something like a product of two modular curves. Now, fix 2 points, x1 and x2 in A1 cross A1. Look at the set tau of x1, comma x2. In fact, let's say look at the set, this union times cross little x2. We range over all possible Hecke correspondences on the first coordinate. Well, then you're going to get A1 cross x2. This is not a Shimura subvariety unless x2 is a CM point. There was no reason for x2 to be a CM point. Such a subvariety is called weakly special. So in general, what you can do is you can have something like S1 cross S2 embedding inside S. You could fix a point in S2, and you could look at S1 cross that inside S. That intersects a Hecke orbit in an infinite set. And so this also is an example of the sort of subvarieties that we've asked for. So these are somehow the obvious examples of subvarieties that display this property. And the conjecture is that every such subvariety has one of these forms. So the Zariski closure of any infinite subset of a Hecke orbit is weakly special. Okay, so there's been a lot of progress made in this conjecture, and it's more or less been fully settled by Yafaev and Rudolph. In fact, who proved not just this, but they prove this conjecture when you replace a Hecke orbit by something called a generalized Hecke orbit. I'm not going to go into what that means, but Yafaev and Rudolph proved this conjecture for all abelian Shimura varieties. By this, I mean that up to replacing S by some sort of cover, it parameterizes families of abelian varieties. Okay. Well, so Jacob's question is that is the missing piece in that argument the fact that maybe they didn't have access to a faulting change of isogeny, change of height and isogeny formula? Okay, fine. So then Jacob's question is actually, is the missing piece in the argument the fact that if you take an isogeny orbit and you intersect it with, say, q points or k points, you get a finite set? The answer is I very much don't know, but they do have a general theorem under some sort of adelic Mumford-Tate hypothesis. So I'm not sure whether that answers your question, but they might use that to prove precisely what you said. Okay. So as my title suggests, I'm going to be talking about things in characteristic P. So let me move to characteristic P. So Shimura varieties, they start off their life over the complex numbers, but then Delin, Milne, Borovoy, they all prove that Shimura varieties descend to an explicitly defined number field. And work of Mumford, Mark himself, and others prove that your Shimura varieties actually can be defined over an integral base. Once you define your Shimura variety over a base like Z or OK, then you can start reducing it mod P. You can ask questions mod P. As it turns out, Hecke operators prime to P, Hecke operators also make sense in characteristic P. So all the words that I've used so far, all of them make sense in characteristic P as well, as long as you're not too crazy about what P you pick. Let's ask the same questions. The first question that I wrote down was a question about equidistribution of Hecke orbits. Now, this doesn't really make sense over FP bar, at least not analytically, because there's no analytic topology. At some point, I'll mention a framework that Mazer suggests that talks about algebraic equidistribution. But for now, let's pretend that there's no way to make sense of polymorphic equidistribution mod P. Fine. But then you can ask, you can work in the setup where you have V a subvariety of a Shimura variety and ask whether you can find a point on your Shimura variety that doesn't lie on your subvariety D, even after moving it around by every single Hecke operator. So now I'm going to, for simplicity, specialize to the case of a G. So one of the questions that you can ask is, let D contained in a G be a subvariety over FP bar. Does there exist a point X in a G such that X take union of all Hecke operators, hit X with every such thing, and you want to avoid D? So maybe you might have expected the answer to be the same as in Car 0, but actually that's not the case. Heuristics developed by Bjorn, as well as myself and Jacob, suggest that this question is a lot more delicate. So let's just assume that everything is ordinary for now. And we expect that, suppose the dimension of D is big enough, and let's say D has maximal monodromy, and let's say that D intersects the ordinary locus of AG in a non-empty way, then every X in AG that's ordinary defined over FP bar is isogenous to some point on D. So this is directly the opposite of what happens in characteristic 0. Now, what do I mean by big enough? We think that big enough should mean that the dimension of D should be bigger than half the dimension of AG. So for instance, if you were to ask the Jacobian question, if you were to work in dimension 4, then the dimension of AG is 10. The Jacobian locus is 9-dimensional. So you expect every abelian 10, you expect every abelian 4-fold over FP bar to be isogenous to some Jacobian. Sorry, I should very much write conjecture. Heuristics suggest the following conjecture. Okay. And there's some evidence for this conjecture, not in the setting of AG, but in the setting of a product of modular curves. So instead of working with AG, just work with a large power of a modular curve. N is, I think, if memory serves me right, N has to be at least 270, but any number should work. The truth should be any number works. Then we construct a divisor that has a property that every x in your ambient space, defined over FP bar, is isogenous to some point on D. So there's some evidence for this conjecture that shows that this question is very different from what happens in characteristic 0. Yes, of course. Exactly.
But I could change. I could take a number divisor and then take another number divisor.
Sorry. So I'm not saying this. I'm not saying we prove this for every D. I'm just saying that we construct an explicit example of D, which has the property that you take any point. Exactly. So that when you move it around by Hecke, you. Yes. Thanks very much for the question. Let me just make that clear. There is an explicit okay. Now here's the thing. Yes. What I think the truth is, so if you take n to be 3, there should be okay. So take n to be anything and take D to be, as long as it has big monodromy, it has dimension bigger than half of Shimura, right? That should be enough. So Jacob would say bigger than equal to should also be enough. Not quite as bold. N can't be 1.
Can it be 2?
Well, if it's 2, then I'd want D to be dimension 1, and that's like equal to half, not bigger than half. And I think Jacob would say yes. I'd say I'd also say yes because Jacob says yes. If you take n to be 3 and the dimension of D to be 2, then I'd certainly say yes.
But your n is bigger. Your n is
Our n is 270. 270. Well, anything bigger than 270. Because once you have 270, you can just take products with more lines.
I'm very curious how this number.
It's 45 times 6.
That explains it.
Exactly. So moving on. So this is something that we can't prove, but well, we haven't thought very hard about it. But I think we should be able to prove that if you take this particular D, not just does it intersect every Hecke orbit, we think it'll intersect every Hecke orbit in a dense set. And this D has big monodromy. It's not weakly special. So this would give a counterexample to the Andre-Pink Zannier conjecture of FP bar. So let me say expect that this D intersects every FP bar Hecke orbit. Let's say every ordinary FP bar Hecke orbit in a Zariski dense set. Okay, so we just want to take the naive formulation of the Andre-Pink Zannier conjecture and just replace C or Q bar by FP bar, it's likely not going to be true. But here's the thing, function fields seem to behave more like number fields than like finite fields in this particular setting, for whatever reason. In fact, Bjorn proves that there exists an abelian variety over FP bar T that's not prime to P isogenous to the Jacobian of any curve. He does this by studying topological properties of Hecke operators in the ordinary locus. But things end up being very complicated if you try to also work with P power Hecke correspondences. So this is a prime to P theorem. And joint work with Zimmerman, we proved that there is an abelian variety over F bar T. It's not isogenous to any Jacobian. And of course, for both of us, we need G to be at least 4. In fact, we proved that if you have any divisor of AG, you can find a function field valued point which doesn't lie, which avoids your divisor even up to all sorts of isogeny. And Bjorn's theorem also works in the setting of an arbitrary D sitting inside AG. All right. So, okay. Instead of working with finite field points, perhaps the right thing to do is to work with function field valued points. And that's indeed what Josh and I do. So okay, I'm going to state my theorem just in the setting of AG, but it works for any Shimura variety of Hodge type, which intersects the ordinary locus of AG. We can probably also do mu ordinary, but it didn't seem worth the effort. But feel free to replace AG by any Shimura variety that sits inside AG that intersects the ordinary locus. So take a point that's defined over a function field, and let's assume it has big monodromy. Then any infinite subset of the Hecke orbit of X is Zariski dense. Up to connected components. Okay. And this reduces without too much effort to a theorem about curves. So let's see over FQ contained in the ordinary locus again. Have big monodromy. Let tau hi be an infinite sequence. Let's say tau I be an infinite sequence of Hecke orbits on AG. And I want to say prime to P Hecke orbits. With degree going to infinity. Let Ci contained in tau I of C be a union of reducible curves. Then the union of Ci is Zariski dense. And of course, even over here, when I say infinite subset of Hecke orbit, I mean infinite subset of the prime to P Hecke orbit. P power Hecke correspondences behave weirdly in characteristic P. Okay. And this theorem is also up to taking connected components. So here's a corollary, here's an immediate corollary, which, as I'll spell out later, is immediate over number field, but not quite as immediate over function fields in characteristic P. So the corollary is to finding abelian varieties not as certain as Jacobians. So let C contained in AG have big monodromy. Then only finitely many Hecke translates of C can be contained in the Torley locus. Non-empty union, let's say. As opposed to taking just one curve, it could also be a singleton. Sure, you're right. Fair enough. So you look at tau I of C, doesn't have to be irreducible. Take any irreducible component, do that for each I. Yes, yes. Okay, you know what? Let's just say that. Okay, does that make sense? Okay, thanks for pointing that out. Okay, so now start off with the curve inside the ordinary locus, which has big monodromy. Then take every possible Hecke correspondence as prime to P, hit your curve with it, look at all possible irreducible curves you get by doing this. Only finitely many of them will land in the Jacobian locus. Okay. Now, before saying anything about how any of these theorems are proved, let me just point out that this sort of result in characteristic zero is extremely easy to prove. Here's how you do it. And this is Pink's idea. So let X be an AG, but now let's say defined over a number field. Let's say K. Such that X has big monodromy. Then any infinite subset of the Hecke orbit of X is Zariski dense in some up to taking connected components. Now, here's how you do this. Take your sequence of Hecke correspondence tau 1, tau 2, tau 3, ... You're looking at tau 1 of X, tau 2 of X, tau 3 of X, so on and so forth. Loosely speaking, each of these sets is going to be stable under the absolute Galois group. So up to finite and bounded, let's say, defect. Each set is one Galois orbit. Well, now if the Zariski closure was smaller than AG, then you can find that the complement is open and it avoids these Hecke orbits. So the point is, sorry, let me say this again. If you take any subset of each tau I of x and take the Zariski closure. So let V be some subvariety that intersects union of tau I of x in an infinite, in a dense set. Then we have that V is going to be defined over Q bar, therefore it's going to descend to some number field. And so V intersected with tau I of x being non-empty tells you, because each of these tau I of x is one Galois orbit, tells you that V is going to intersect each tau I of x in a positive proportion of points. This is bounded away from 0. But the complement of V has full volume, and this contradicts equidistribution. The point is, if such a V intersects a Hecke orbit, like intersects infinitely many tau I of x's, it has to contain more or less every single tau I of x, just because of the fact that each tau I of x is one Galois orbit, and that contradicts equidistribution. So this is a really nice and simple argument by Pink that works over number fields, but over a function field, you don't have any notion of equidistribution. So this is not going to work over FP bar. So let me briefly say a little bit about a different notion of equidistribution that Mazur formulates. And it has to be an algebraic notion for obvious reasons. This formulation is due to Mazur. So what Mazur says is, let tau I be a sequence of Hecke operators. Let's say, yeah, sequence of Hecke operators, and then we say that tau I of C equidistributes if the degree of hi goes to infinity, where hi is the minimal degree hypersurface that contains tau I of C. So you take C and you hit it with more and more and more Hecke correspondences. At every stage, you look at, well, at every stage, you're still going to get a curve, but maybe the curve is getting more and more and more twisty. So you look at the smallest degree hypersurface that contains your curve at the ith stage, and you say that your sequence of curves equidistributes if the smallest degree goes to infinity. And this being true for curves with large monodromy is an immediate consequence of our Andre-Pink Zannier theorem. So let's see contained in AG half-peak monodromy. Let di be the minimal degree of some hypersurface containing tau I of C, then di goes to infinity. All right. Okay, so now might be a good time for me to pause for questions, if there's any.
What
Good question. So on AG, you have a family of abelian varieties, and you can look at the Algebraic monodromy of your family. I just want to say that C has the same Algebraic monodromy, at least as far as QL is concerned, not necessarily ZL. Like you could have the monodromy of C could be finite index in the monodromy of AG, but to be finite index, the dimension shouldn't be smaller. So for instance, you're not allowed, the generic abelian variety parameterized by C cannot have extra endomorphisms. Pull it back to C. Ask for it to have big monodromy. Exactly.
Okay, so then what do you ask about the image of this?
Ask for it to be Zariski dense in GSP to G of QL. Yes. So, but then that that gives you openness, at least in SP, in SP to G of ZL.
Okay. So this rules out C being inside of any kind of special locus.
This rules out C being inside of any special locus, and conjecturally, the opposite should also be true. Great question. Jordan.
So even though you can't conclude this statement of the effects of all one element except for a finite value defect, is that still true?
The intersection of what and what? Yes. Yes, yes. Correct. Yes, it is. Yes, it is. It absolutely is. That's a great question. That's sort of why we work with big monodromy in the first place. Yes, indeed. Okay, so in fact, these questions that you asked sort of lead me to the first step of the proof. So going from big monodromy to going from maximal monodromy is actually not very hard. So let's see. Let me write some setup. So let's see I contained in tau I of C be as the theorem. Let's say V is the Zariski closure of the union of the CIs. First step is to reduce to the case that C has maximal monodromy. By replacing S by a suitable level cover. In order to do this, we need a certain idyllic open image theorem that's proved by Cadoret and her collaborators, as well as the companion theorem proved by Bockel and her collaborators. So now I'm going to assume that after having replaced AG by a finite level cover, even integrally, the monodromy of the universal abelian scheme over AG is the same as the pullback to C. Okay, and then you use maximality of monodromy and degree arguments to pass from saying that your CIs are to go from saying that V contains a big Hecke orbit to saying that V is actually stable under some Hecke correspondence. So I should say, instead of working with a perhaps thin set of sequence of Hecke orbits, if you were to work with all Hecke orbits, then it just follows that V is stable under Hecke correspondences. And so in that case, you get this for free. And once you have this, life becomes a bit easier. But using the maximal monodromy hypothesis, we can show that V is stable under some Hecke correspondence. Okay. Then we use the Chebyshev type here, Chebyshev type arguments. And of course, use big monodromy again to find points which, first of all, are stable under the same Hecke operator. This is not hard. And we also insist that X is a so-called while CM point. Now, this is a group theoretic notion that Chai and Oat define. Let me just say in words what it means in the case of AG. So every abelian variety mod P is special. So it's going to have CM. Now, the generic case is that you have CM, is that your whole endomorphism ring is, your whole endomorphism algebra is going to be a degree 2G CM field. Saying that it's while CM means that the Galois group of your degree 2G CM field is as big as possible. The biggest it can be is going to equal the while group of SP2G. So that means the totally real degree G field has to be an SG field. Its Galois group has to be SG, and then the Galois group of the CM field has to be SG semi-direct product Z mod 2G to the G. That's the while group of the symplectic group, and this is something that we can do that we end up doing for any subvariety of any ordinary Shimura variety of Hodge type. And this gives another proof of Chai-Oat's theorem that while CM points are very abundant in Shimura varieties. And this is a characteristic P proof. Now, here's a consequence of, well, maybe I don't have time to talk about why this is important. Let me just say that after this, we do a local analysis at X. We use certate coordinates and the fact that if you take the completion of V at your point X, it being Hecke stable, this follows, and this makes sense because X is a fixed point of your Hecke correspondence. The fact that your point ends up being a while CM point tells you that your Vx has to be a subtorus in the certate group structure. Now, in general, if you want this to be true, you need every single Hecke correspondence fixing X to stabilize Vx for this to be true. But because X is a while CM point, it ends up that even having one non-trivial Hecke correspondence fixing Vx is enough. Okay, and then finally, so this uses a rigidity argument, a rigidity theorem by Chai. But in order for this to be applicable, we need the point to be while CM. It's not going to be true otherwise. And then finally, once we're in the setup, work of Marco D'Adazio, who proves the parabolicity conjecture. On isocrystals, plus being a subtorus, tells you that the dimension of your V has to equal the dimension of your Shimura variety. And then you're done. And this idea was due to Paul van Hoften. This is how he proves the ordinary Hecke orbit conjecture. It was his idea to use Marco's proof of the parabolicity conjecture. All right, let me stop here. Thank you for your attention.
I'm sure you mentioned this already, but what sort of transcendence input do you have on the certain coordinates to make the argument work, or do you not need anything?
Do you mean for 4 or for 5? Proving that you're a set subtorus, or deducing that you're everything if you're a set subtorus?
I guess either, maybe, yeah.
Well, okay. Okay, fine. So here's what Chai proves. Chai proves that if you take any formal subtorus, you take, and then you take, let's say, a smooth formal subscheme of your formal torus. Now, if it's stable under a big enough automorphism group of your subtorus, if it's stable under a big enough automorphism group of your torus, then it has to be a subtorus. That's what he calls the rigidity theorem. I wouldn't call that a transcendence input. It's just a really beautiful theorem that he proves and he uses. Okay, sorry. So we're actually working in a formal subtorus in characteristic P, so there's no torsion points. But you're right. Otherwise, you'd have to say translate. And then I'm not going to say what Marco Diatasio's work gives you, but well, maybe I am. So if you were to look at the p-adic monodromy of your family for abelian varieties, namely the monodromy of your F crystal, what Chai and Paul and Marco, what their work gives you is that if you were to look at the unipotent part of your p-adic monodromy, and it's going to be a parabolic because you're ordinary and so you have a slow filtration, that actually has to be, first of all, as big as the smallest celtate subtorus containing your formal subscheme, and so therefore it's going to equal the set subtorus, and it's also going to equal, and if your alaric monodromy is maximal, then that has to be everything.
Okay, but you're never, it seems like you're never in a situation where you're intersecting subtori with tangents or home completions of varieties. You're only ever one containing the other, and you want to know if they're sort of equal. That kind of
Correct.
stuff. Okay.
Correct. I think my student Rofan might have work to do with, he's work in progress to do with intersections and sorts of things you're talking about, but you should ask him at some point. Thank you.